Today's episode of Hansel Minutes is sponsored by Datadog. With infrastructure monitoring, distributed tracing, and logs, Datadog provides end-to-end visibility into the health and performance of modern applications. Datadog's distributed tracing and APM generates detailed flame graphs from real requests, enabling you to visualize how requests propagate through your distributed infrastructure. You can see which services or calls are generating errors or contributing to overall latency, and dive deeper into your production code with an always-on code profiler to pinpoint the root cause and optimize your application faster at no additional overhead, regardless of your scale. Start monitoring your applications with a free trial. datadoghq.com/HanselMinutes. That's datadoghq.com/HanselMinutes. Friends, I'm Scott Hansel, and this is another episode of Hansel Minutes. Today I'm talking with George Lee. He's an electrical engineer with a specialization in RF communications, and he's working on MiTEE, which is an amazing new satellite platform that I'm going to learn all about today. How are you, sir?
I am good. How are you?
I'm pretty good. So where are you calling from?
I'm calling from the Big Apple, New York City.
Okay. Now, are you working on this on behalf of NASA, on behalf of JPL, on behalf of the University of Michigan, all of the above? Can you explain the relationship between all these different organizations?
Yes. So I am technically employed by JPL, but I joined the MiTEE project when I was still studying there as a master's student for, it's like a master's student research project. So MiTEE is, the project is owned by the University of Michigan. But the launch provider was the launch provider as well as the key sponsor of the project is NASA, JPL, as well as NASA. Here's the distinction: NASA JPL is technically run by Caltech, the California Institute of Technology in California, Pasadena, and it's run by them for NASA. So it is a subsidiary of NASA, but there are different rules and different projects and missions coming out of JPL than NASA as a bigger entity.
Interesting. Okay, so when we the lay people, the non-space people, are thinking about how stuff gets into space, we're imagining just really smart people at NASA inventing stuff and then throwing it up really high with rocket ships. But in fact, it's a series of partnerships between academia, between the government, and sometimes even people like SpaceX.
Yes, so I would say actually that the vast majority of satellites that are going up, if they're not commercial, i.e. for communications or SpaceX, their international Wi-Fi beam from the sky concept, then the majority of stuff that's going up is actually partnerships between universities and either NASA directly or to the JPL lab. It's fast. It depends based on who's giving the funding and, the specifics of your project, your mission.
When lay people think about satellites, we think about things that are the size of like a minibus, like 7-10 meters wide. You're throwing a car in the air and then it's basically falling perpetually around the Earth. But MiTEE is a series of cube satellites. What is a CubeSat?
So a CubeSat has more recently in the life's sort of recent history has been defined as a standard in the size of a satellite. So traditionally, satellites are kind of, as you said, all over the place. Some are huge, some are tiny, they're just kind of big. CubeSats has been a recent movement to make satellites smaller and smaller. And a CubeSat the standard is basically one cube in a satellite is what we call a unit, 1U. And each unit is a cube that is 10 centimeters by 10 centimeters by 10 centimeters. And it has a maximum weight of 1.3 kilograms per cube. And basically, a CubeSat can be made up of several of these units. So for example, MiTEE is a 3unit CubeSat. So it's 3 of these cubes stacked up like a loaf of bread. And you have certain standard sizes of CubeSats. So you have, for example, 1U, just a cube by itself, 2U, 3U, and then from there you might go 6U, which is 2 loaves of bread stuck together, the long way around. So you get 6U, and then you might have 8U or 16U, and basically allows the launch providers to create standard sort of pods that these CubeSats can fit in, and it's just easier.
So it's container ships for space.
Yeah, it's basically containers for space.
Interesting. So by focusing on the notion of a unit, now when I think of a unit myself as a programmer, I think about a 1U rack server, and I recently installed a 19U rack so that I can fit multiple. Some of my racks are 1U, some are 3U, just kind of like you described, where that unit is standardized. On a container ship, they're a specific size because everyone agrees. Then the things that pick them up are the same. The ships are all the same. Everyone can count on that. Is there a minimum number of cubes that one satellite bunch needs to have? Because you can't really throw a 3-pound thing around the Earth, right? And just have it be fine all by itself.
1U, right?
You can have a 1U CubeSat and just that's it?
So we actually had 3 1U satellites on the same mission, the same launch as us. 2 of them were, can't remember the name, Polar Cube, I think. And they're basically a 1U cube with a camera on all 6 sides, and it's designed to take photos. I'm not going to speak on behalf of the mission, but
of course,
yeah.
But are they allowed? Are they attached to each other, or are they all alone in space?
They're just a little cube just floating around. Yeah.
Somehow I thought it was like Minecraft, and they would be stuck to each other
to form a 3U.
To form a 3x3x3 cube.
When it's launched, because the majority of the cubes, the satellites on our launch with Virgin Orbit were 3U. So the launcher pod, the delivery pods, was a 2 rows of 4 3U satellites side by side.
Yeah.
And so they just put the 3 1U satellites into one pod, just stack them in there, so that when they get ejected, then three little 1U CubeSats go out flying into space.
I'll put links in the show notes, but folks can go and see pictures of these. And what's shocking about it is that you can see one of these being like basically held by someone in their hand. And I don't mean to imply that there's not like amazing future technology in these things, but it kind of looks like a bunch of Raspberry Pis and some lithium batteries in a rack, in a mini rack. There's got to be more magic to that, right? Is this really off the shelf? Does this make like satellites available to more people than ever before?
I wouldn't say completely off the shelf. It is off the shelf in the sense that the framework can generally be copy and pasted because it's been standardized to 1U, 3U. But of course, according to what your mission is, all the electronics inside will most likely be custom. The only things that probably aren't custom are the battery cells, maybe your radio, some of the microprocessors and things that you will be putting on top of your PCB boards. But all of that is, the components themselves might be off the shelf, but you have to put them together yourself. Yeah.
That's amazing. I went and I searched for 3U CubeSat structure, not the satellite itself, but the structure within which it would have. And there's a company in the Netherlands that will sell me one for €4,000, which is a lot of money, but we're talking about spaceships here.
Well,
so that's
when you're
pretty
paying
awesome.
$20,000 a kilogram to send something to space, that's change. That's pocket change. And compared to traditional costs of launch, CubeSats are a big deal in terms of education and university research.
Yeah. And one of the other neat things about this, which I feel is so exciting, is because it makes it not necessarily more accessible in that I and my children are going to throw a satellite up in the air, but I can actually go to CubeSatKit.com, download publicly available CAD models, 3D print one of these, and get a sense of what it felt like. So if I was teaching school, I was teaching this to science kids, I could say, here's a 3D printed feel. This is what a satellite is. This is not to scale. Like it's 1-to-1 to scale.
You can go to Home Depot like we did and put some Stanley tape measures on them as antennas. And we actually tested a whole series. I've been getting a lot of this on my TikTok, name drop.
We'll make sure to include links to George's TikTok as well.
And I made a video post about showing our tape measure antennas, and I can't remember the exact brand. I said Stanley in the video. That's not technically correct.
Are these literal antennas or are these like prototypes? This is like what you
No,
used
this
to
is
show.
on-flight hardware, and you can see it in the photos from Virgin Orbit's media release, from the payload from the rocket just before they were released into space, and you can see a little dash of yellow. That's our yellow tape measure antennas.
I'm going to make sure to include links to that as well, because this CubeSat that's going to be testing out and exploring Earth's magnetic field, it uses that magnetic field for propulsion rather, and generates the thrust off of that. Is that right?
Yes, that is correct. It's quite cool. Our primary mission is a technological advancement proof of concept mission. There are a few different types of missions you can have when you send a satellite up into space. Some of it's, imaging, either the Earth or the universe. Some of it's communications, defense, that's its own thing. And then the other big one is technological proof of concepts, technological advancement. So ours, MiTEE 1, is a proof of concept of a fuelless propulsion system. It doesn't use fuel. Traditionally, when you send a satellite up to space, you have to include some fuel up if you want it. You have to include some fuel with it if you want it to last in orbit for any period of time, any long period of time, particularly in low Earth orbit, where there's a lot of atmospheric drag, and over time, your satellite will fall back down to Earth. So you have to include some fuel to maintain your orbit. We call it orbital station keeping. So what we did is we're using an electrodynamic tether. It's basically one really long, 30-meter long conducting wire. It's insulated out from space, but on either ends are open contacts. And we use the open contacts along with the Earth's ionosphere to create a closed circuit. And if you think back to sort of high school physics, if you have a current moving through a wire, and you put that wire inside a magnetic field, then you end up with a net force exerted on that wire, either one way or the other. So that's the basic concept that we are using on a larger scale to provide some force to maintain the speed of your satellite when it's in orbit.
Forget dozens of visualization tools and view your entire system in one place with New Relic Explorer, the latest addition to New Relic 1. See your system-wide health at a glance with a dense hex view that has your hosts, services, containers, and everything else. You can get an estate-wide view of sudden changes, so you can catch issues before they impact customers. Go to newrelic.com, sign up for free, and start exploring your system today. So the ionosphere, the ionized part of the Earth's upper atmosphere, from like 30 miles up till a couple 500-600 miles up, it's ionized by solar radiation. So you've got that long tether. It's collecting current, but what kind of current are we talking about? Are we talking about charging a lithium-ion battery amount of current? Are we talking about milliamps, full amps?
We're talking probably milliamps to 0 point something amps.
I see. So it's not like shock yourself, put your finger in the mains.
No, you won't feel that
amount of power.
No.
Okay, and then it takes that and it stores it, and then does what with it? How does it convert that energized radiation, that solar radiation that gets ionized the ionosphere, that turns into atmospheric electricity, and then gets into a battery, and then you do what to push forward?
So if you imagine you have to have a picture of our satellite. So we have a 3U satellite. Out the bottom is a big long piece of string, and at the end of that string is another little mass. So at the bottom there, where that mass is, we call it a picosat, which is pico being an order of magnitude smaller than the normal 3U satellite.
Mm-hmm.
And then we have down there what are basically electron collectors. They collect electrons from the ionosphere, or they accept electrons. What is that, cathode?
Mm-hmm.
Yeah, cathode. And cats are positive. Yeah, cathode. So it accepts electrons from the ionosphere, and then we drive those electrons up the tether, which forms a current. So a current in your computer or in your light is just electrons moving in one direction. So we just drive those electrons up the tether, and then once it reaches the top of the tether, it reaches our CubeSat, and then we have the anode, the electron emitters, and we shoot those electrons back out into the atmosphere. And this creates a sort of a plasma, a net. Yeah, for lack of a better term, it sort of sets one side of the... How do you say this?
Well, so let me see if I can understand from a layperson's perspective. This isn't blue plasma shooting out of the back of Princess Leia's ship.
No.
But it is an invisible stream of electrons that's coming out of one side, which then sets a negative effect on the other side.
Yes,
thereby.
Exactly. Yeah. Biasing. That's the term I was reaching for. You bias each side of the picosat, the end body, with this the main satellite unit, and you bias them in opposite directions so that you encourage a current to flow up the tether.
So when I think about spaceships, as again, I keep saying as a layperson, I'm imagining huge amounts of thrust. I'm imagining stabilizing thrusters where it's like, oh, we're spinning out of control. Where it's like huge amounts of thrust to bring me back. Is this putting out just generally stabilizing thrust, or are there moments where it's like, oh crap, it's spinning out of control, we have to do something? Amounts of thrust.
So you will not be able to stop anything from happening with this. This is sort of... This requires time to work. We're talking micronewtons of force, which over time will be able to maintain your speed in orbit.
Interesting. I've heard about ion drives being a thing that we're going to talk about that can really get us up to speed, but it's a slow burn, literally.
Yeah, so SpaceX's Starlink has some ion thrusters, and they use a similar, a completely different concept, but they use...
only in that ions are involved, I guess.
Yeah, they use the similar concept in that it takes time for that tiny amount of force to be able to offset your otherwise drag. Yeah.
When you have something so small, still, I mean, the size of a bread box, really, and I will include pictures. There's a great picture on newatlas.com where the MiTEE 1 is undergoing acoustic testing, and you can actually see outside of it. Chamber. Yeah, you can see the bits of metal from the Home Depot.
Yeah, the tape measures
and stuff. It's something that a human could pick up with some awkwardness and throw. How is it not spinning wildly out of control when it's up there? I realize that it's not truly the atmosphere, but it's kind of the atmosphere. There's no wind.
There is still atmosphere. There's still drag up there.
Yeah.
So that's where attitude control comes in. Attitude being slightly different from altitude. Everyone knows what altitude is. That's how high you are off the ground. Attitude is your direction in relation to, in this case, Earth. So what we want to do is we want to keep the entire, the string, the mass on the end, the CubeSat, we want that to all be perpendicular to the planet. So we use, actually passively, we use what's called a gravity gradient to maintain our attitude. So a gravity gradient comes into effect when you have something that is quite long. And what happens is when you're at different altitudes relative to Earth, you have a different amount of gravity affecting you. So if you have, in our case, an end body that is 10 to 30 meters closer to Earth than the main satellite body, it's got a much stronger gravity affecting it than the body up here. So what happens in effect is, if you were to imagine tying a mass to the end of a string and spinning it around your head, you have effectively the same thing. Gravity is grabbing hold strongly to this tiny mass at the closer to it, and then spinning the larger mass around the planet.
So does that mean that the heavy part of the satellite is facing away from the Earth, and you've got centripetal force basically swinging it around the Earth?
Mm-hmm. So if you look at, actually, if you go to our satellite dashboard, which is public access, by the way, you can see on the gyros and the accelerometers that there's constantly a force being exerted in the z direction.
Interesting.
It's 0.00 something, but it's a little bit there. And then to supplement that, we have magnetorquers on board as well to maintain anything that the gravity gradient can't do. Yeah.
Wow. So the dashboard itself is available. Like all of this is happening for the betterment of humanity.
Yeah, I mean the information is completely, well, the beacon, the telemetry data is mostly open source.
Mm-hmm.
The actual primary mission data, that's well, it requires some decoding, so we can't actually give that out to everyone. But in terms of, what the battery voltages are, the activity from the photodiodes, the temperatures, the readings from the accelerometers, everyone can go and check that out online as well.
That's cool. I would love to have the link to that as well. One of the things that I was learning about as I explore not just CubeSats but satellites in general is that there is both amazing future technology it's the 21st century, we're in 2021 here, but there's also older things like how satellites are thought about. There's a thing called a two-line element, which is kind of like the latitude and longitude of a satellite.
Mm-hmm.
That's almost 60 or 70 years old.
Yeah.
Is satellite technology both in the past and in the future at the same time?
I would say it's being built upon things that have worked well in the past,
mm-hmm.
and I wouldn't say it's. I would say that at some point you would have to move off of old things. The TLE, for example, that goes back. That's a throwback way to early '60s, before digital computers were really a thing, and you had to use basically punch cards. That you might have used something similar if you're in college recently, and you fill in the bubbles, and then it's a scantron, and then you fill in the bubbles to A, B, C, D, E for your answer, and then a computer scans it. In a similar way, they used to use punch cards, and it punches holes in the card, which can then be scanned by another computer, and that was how you transferred information from one computer to another. So TLEs, two-line elements, were basically originally designed for a punch card with 80 lines on it, and it would document a certain orbital body and its current location, its predicted future location, its name, the time that this reading was taken, etc., etc. Yeah, so things like that, they have just been adapted from previous use. But I would say, TLE is an interesting thing because eventually we're going to run out of characters to name new satellites. Every time a new satellite goes up, you increment the number by one. And eventually you're going to have sort of like a YouTube situation where, like Gangnam Style had too many views for their 32-bit counter. You're going to reach, what's it called, int max in C.
Yeah.
And then you're going to have to change. So, they changed the 64-bit. At some point, TLE will have to change to probably something a bit more modern.
Yeah, it's worth pointing out that, in 2012, 2010, there were just maybe 100 CubeSats out there, nano satellites and CubeSats. And now we're, very, very quickly approaching 4,000 plus. There's a lot of stuff flying around the Earth up there. How do we talk to these, though? It's not Wi-Fi. What's the RF communications expression of the data? Are you just yelling as it runs screaming around the Earth? Is it just shouting RF information and trying to tell us what's going on?
I mean, in a nutshell, it basically is. It is screaming RF sort of into the void, but it's screaming it at a very specific frequency. So for a lot of research projects, they tend to use what we call the amateur band in frequency in electromagnetics. The amateur band is what's been allocated in the electromagnetic spectrum for use for people at home to communicate with each other on their radios, basically anything that's not federal or commercial use, you can put it in the amateur band. So a lot of research projects sit in that band, and our satellite is one of them. 437.8, by the way, if you're a hammy out there and you want to listen in. And it's a very specific RF frequency, and that allows you to put many different frequencies. You can split up. Everyone can use a separate frequency, and then you don't get any talk over or clatter or interference between frequencies.
Yeah. Do you have to ask permission? Like if you were going to start a new cell phone company or a new television, you have to go and, park yourself in the RF spectrum somewhere. Do you have to go and make sure that there's a spot for you when you throw your satellite into the air?
So we have in America what's called the FCC, Federal Communications Commission, something along those lines. And yeah, you have to go apply for a license with them. It's a long bureaucratic sort of, drowning in paperwork sort of process. But yeah, anyone can do it.
Now that you're doing things remotely, I assume you're stuck at home just like the rest of us. Are there people, is everyone just at their homes with giant computers trying to look at the data? Like, what are you working on a day-by-day basis from your home office?
So for me, I am more on the R&D side. So I don't need to crunch any numbers from the satellite, the mission itself. I am just developing whatever. At the moment, I'm working on MiTEE 2, the second iteration of the satellite. And we're looking at using this tether as a second source of communication, as a second antenna, basically. And we're running models on that. But yeah, it depends on what you're doing. The people in ODAX or orbital mechanics, they're crunching numbers. The people in plasma, they're downloading data and doing their research. But yeah, I don't think you need a huge computer for it. Mostly, it's just depends on what simulations you're running.
Do you need a huge team? How many people does it take to put a CubeSat into, if I decided to like assemble a team right now with my local university?
So it depends largely on what your mission is, but I would say probably no less than 50 minimum. And that would be sort of full-time working on the satellite. For MiTEE, this has been over a decade, and because it's open to undergraduates as well, we have a revolving door. I say revolving every 4 years door of undergraduate students. Some of them stay on, and it's added up to probably close to 300 people who have had some sort of contribution to this CubeSat over its 10-decade R&D cycle. Yeah.
10 years?
10 years. 10 years. 10 decades. 10
I was
years.
just saying, it's a century-old satellite.
10 years, yeah.
Yeah, but it sounds like this is how do you even test this? Because what's interesting about MiTEE specifically is that you're testing a way of doing propulsion, but you can't really truly test it until it's up there.
Yeah, this does not work on Earth.
How do you even prove the concept? Like you threw this cube into the air, and the only way that you knew it might work was math.
Basically, some physicists and their blackboards. Yes, we still use blackboards, and they were crunching numbers for years, for many years. This concept has been around in sort of academia for quite a long time, and it's some people's life's work. But yeah, there was zero way to test this on Earth until we sent it up. It's just
that's awesome,
pure hypothesis.
And back to the RF, how much do you have to think about power? Because you've got this thing is actually trying to prove that it can generate power. But if it couldn't generate power, was it just going to fall out of the sky? Or do you have batteries or solar as a backup in case? Because you have other things you have to do. You have to generate enough to move, but then you have to live as well.
It's got a 25-week lifespan. And after that, it's got no fuel. It will just come crashing back down to Earth and burn up in the atmosphere.
Oh, interesting.
So, either way, this mission was going to be 25 weeks long, regardless of whether the data worked out or not. But yeah, it's completely 25 weeks.
And it's not going to hit me on the head, though.
No, it'll burn up in the atmosphere for sure. Yeah.
That's kind of sad, actually.
It is a little bit sad. Yeah.
So I found you on TikTok, where I have been finding a lot of really cool people. I didn't know what my TikTok was going to be about when I started. And I noticed that your TikTok, which is really, really interesting, and you should check it out, talks about NASA and MITE and electrical engineer, but it's actually called George Lee Photo. You thought you were going to be talking about photography.
Yeah. I mean, I've been doing photography since before I started my engineering career, way back in high school, back in New Zealand. And I've been working as a commercial photographer well before I got my degree in engineering, and it's sort of followed me all the way until now. So yeah, originally that TikTok and most of my social media is for photography. Yeah,
but now you're on Space Talk forever.
Yeah, I'm Space Talk now. It's a strange place to be. Yeah.
It's great though, because people are just enjoying it. And what's nice about it is that you have really fun conversations. I can see conversations about different shapes, about you have an example where you show a satellite versus a cooking wok.
Yeah. So I was that originally came about because I was showing some of the 3D simulations I would have to do, modeling the propagation, the radio wave propagation from certain types of antennas. And I showed a quick example of something that I might have to do for a mission like MiTEE. And it creates this really cool 3D sort of shape, which people found interesting. And then some people said, oh, can you do the Yagi antennas? This is from ham radio operators on Earth. I want to see what my Yagi antenna looks like. Mm-hmm. And then it just became a joke, because, what if you did the Pringles cantenna? The Pringles can put a Wi-Fi antenna in it and beam your Wi-Fi across the road to your friend, three buildings down, or, scream at your neighbor in radio waves. And I did that. And then as a joke, someone said, what if you used a wok as the reflector? And I said, all right, sure, I'll model that. And yeah, it's quite interesting. I live for some interesting suggestions.
That's one of the great things that I'm enjoying about TikTok, is that once you get, no disrespect to people who like the creative dances and stuff and the memes, but once you like enough stuff, it takes a couple of days to get past the inappropriate content. TikTok figures out who you are.
Yeah.
And it's like, okay, you're a huge nerd. Let's talk about what the RF characteristics of a wok are.
It's such a strange place to be on TikTok.
And it's wonderful and creative, though.
Yeah, it's something that people can't necessarily do at home. The software that we use is, a license is $40,000 for a license. It's insane. So,
but it speaks to getting space accessible to people, and that's what's great about working on a project like this.
Yeah.
Fantastic. Well, thank you so much for chatting with me today.
Of course.
You can check out George Lee at tiktok.com/@GeorgeLeePhoto. I'm going to include links to that, as well as lots of links to things like NASA CubeSats, the project at the University of Michigan in Ann Arbor, pictures of the spacecraft itself, and hopefully a dashboard if I can get a hold of that link as well. This has been another episode of Hansel Minutes, and we'll see you again next week.